the deflections, and then we talk about this is the failure series, and both for cyclic and also this is a static loading. And we also have talked about our first component, which is the shaft, which is one of the most important components in this is mechanical engineering. And today we are going to talk about our second one and talk about the screws and fasteners and design of non-permanent joints. And so my bottom line is that, and we are as a mechanical engineer, and we should be able to calculate using our hands or using the abacus, FEM, and to calculate the strength or the deflection stiffness of the joint is the components if we use these screws and fasteners. So I'm going to give you an example, not today, and this is Monday. So that example is very, very important. And also, by this is the next Monday, I'm going to tell you what will be covered in our exam too. Okay? So you have a better understanding. You take a look at the examples I just taught. Make sure you understand all these examples. If you cannot, if you do not understand or have some any confusions, you are supposed to come to see me before I send out the exam. So the screws and fasteners, and so we have, I think we have handled these kind of things in our daily life. And screws, we know the screws, right? So why we need to use this is non-permanent fasteners. A non-permanent fasteners, as the name suggests, it means that we can easily assemble these things together, use this is the fasteners, and then we can just disassemble it and just separate. So this is, on the contrary, there is a permanent fastener. A permanent fastener, for example, the welding. And we are going to talk about welding after we finish this topic. For the welding, when we weld the two things together, it is usually very difficult for you to break it. You guys agree? For here, if we use a screw, and we just use the driver. This is the we can just easily to assemble these things together and then disassemble them separately. So for the permanent fastener, it's very, very almost physically we say impossible unless you break it. Right? You guys agree? Doing great? And then I will give you a task. I weld those two things together. I'll ask you to separate without damaging any of them. It's totally impossible, right? So, so what is the reasons for field assemble? We assemble different separate components together, and we disassembly, this is maintenance for maintenance and for adjustment. And so for adjustment to reduce this is the residual stress, or just make sure all these parts they have the same comparable amount of residual stress. So I do not know whether you guys have ever heard this story. And so when we just assemble these two pieces together, okay? I don't know if you have this experience or not. When we assemble these two pieces together, let's suppose we have two plates, and we have eight bolts and 8 nuts, 8 pairs of bolts and nuts. And what is the correct way to assemble them? The correct way means that we want to minimize the distortion and minimize the stress concentration. Can somebody tell me, if I give you this task, how are you going to assemble them correctly? Correctly means minimize the distortion and minimize the stress concentration. Can somebody tell me? You can make a guess. No punishment, please. You have never done this for your parents? Unbelievable. Okay, usually the correct way, okay? Correct way is that I just assembled all these 8 pairs of bolts and nuts, slightly, okay, slightly, I will not fasten anyone very, very tightly. And then I do these things one by one, make sure at the very, very end, almost all these 8 pairs of bolts and nuts, they reach the highest stress and stiffness together. So this is the bottom line. Have you guys ever heard this or? Okay. So on the contrary, if you just use for the first pair of bolts and nuts, if you assemble them very tightly, and then so these 2 plates will deform, right? So the stress concentration, and then no matter how you assemble all other pairs of bolts and nuts, and here the first pair of bolts and nuts, you will have a heavy stress concentration factor. Don't believe me? And you can use abacus to take a look at this stress concentration. And by the way, guys, the experiments. For the experiments, we only know the results, but we do not know the stress distribution and strain distribution. You guys agree in the process? But when we use abacus to model it, and we can see clearly the history of the stress change and the strain change. So that's the beauty of simulations. I'm advocating the simulations. So the thread. And thread is the commonly seen component in our daily life. And I don't believe, and if you tell me I have never seen threads, I don't believe. Because this is in our daily life, and you drive cars, right? You know this. And I think maybe you have helped your parents assemble some doors, windows. You know this. Maybe tables. You know this. So this is our old friends. This is our friendship. So this is the thread. It's a thread, and there are several important concepts here. You can see, one is called pitch, and the pitch. I would like you guys to understand this one. Pitch is a very, very important concept in machine design. So not just here, but also for the gears. Right? For the gears, we know we have multiple teeth on the periphery of these circles. So here's a pitch. What's a pitch? Pitch is distance between a distant thread. A distant thread from these 2 guys. So this is the pitch. And same thing for the teeth, okay? For the gears. For the multiple teeth, we can just see that is a pitch. We call the pitch also. So I want you guys to underscore this one, know that this is a very, very important concept. Reciprocal of stress per inch. So this is reciprocal of the stress per inch. So major diameter. Major diameter, largest diameter of the thread. Largest diameter of the thread. From here to here. The largest diameter of the thread. From here to here. And so also have a minimum minor diameter. Minor diameter is the smallest diameter, is from the root. Right? And from the root, so this is called minor diameter. And from the top, it's called major diameter. So minor diameter, major diameter, along with the pitch diameter, and we have the same concepts for our gears. And we will talk about the gears later. Gears are very, very important, and we will spend several class sessions for gears. I want you guys to know. And the pitch diameter, so here's the pitch diameter. And pitch diameter is from here to here. What is the pitch diameter? And theoretical diameter between major and minor diameter, where tools and caps are same width. So what is a pitch? So this is a pitch. And what is a pitch diameter? And pitch diameter means that I draw a line, okay? I draw a line that is parallel to the axis. This line such that this line from here to here, that is the thickness of the tooth equals the gap between the teeth. So this line. So I draw a horizontal line which is parallel to the axis, center line. And such that this line on this line, so the thickness of the tooth equals the gap between the teeth. So this is how we define the pitch diameter. You guys understand? And pitch diameter, they're two different concepts. Question.
This might be a dumb question, but what about square threads? Like, where do you measure from there?
Say again?
Like square threads? Like, these are like triangle threads, what if they're like square? Where do you measure from? Is it the center of each?
Yes. For square also, and you need to draw a line on which, so the thickness of the tooth equals the gap between two teeth. The same thing. That's good question. We talk about this one for the next slide. Very good question. So this is Aiden, right?
Yeah.
Aiden just mentioned, what if the teeth profile is not this one? It is the square teeth. The same thing. And we also draw a line such that on this line, the tooth thickness or tooth width equals the gap between two teeth. And we call this one as this line. This here is one line, here is another line. So this is called the diameter, pitch diameter. Pitch diameter, major diameter, minor diameter along pitch. I want you guys to be able to use your own language to tell me if I draw this one in exam 2 and I remove all these things, ask you guys to label these 4 concepts, and you should be able to do that, right? Okay, good. So standardization, and the standardization is very, very important. Why we need to use the standardized this component? Because of the cost, low cost, right? Do you guys agree? If these components they are produced in mass production, that means that the cost will be very, very low. That's the reason, and we want to use standardized components. So standardization. So this is the National Thread Standard defines the basic thread geometry for uniformity and interchangeability. Interchangeability means that you can buy this if you want to buy a thread, and you can either from this vendor or for that vendor. Supposedly, they should give you the same thing. But no, I should not say the same thing. I should give you 2 sets of components that both satisfy your needs. Otherwise, this vendor will go bankrupt very quickly. Okay? Because they cannot satisfy the customer's needs, and it's very, very important. So next one, American National Unified Thread, we have several. And UN is a normal thread, and UNR the root radius for fatigue application. So this is a special. This is a normal one. This is special and to enhance the fatigue life for fatigue applications. So metric thread. So these American, so these US customer need these units. For these metric units, and we also have normal threads and a greater root radius. So this system and this system we have 2 categories. For this system, and we have also 2 categories, and they are corresponding. But when you go to the Lowe's or this Home Depot, if you want to buy some threads, and you need to tell people whether it's the metric or the US customer, right? So this is the core series. You will see this core series. I mean the tools is huge, is big. This is for general assembly. Frequent piece assembly, not good for vibration because the tools are too big. The normal thread to specify. And fine series means that the teeth they are relatively smaller, and good for vibrations and good for adjustments. And for automotive and aircraft, people usually use the fine series. Extra fine series good for shock and large vibrations. And high-grade alloys, instrumentation means this is different. This is the small devices, for example, sensors, or other. This is a characterization equipment. For example, TEM, ICM, this kind of very, very sophisticated devices or included aircraft. And for these military aircraft, which and very sophisticated, you usually use extra fine this series of these threads. So here basic profile for metric. Metric is using international units. MG threads are shown in this picture. So the table 8-1 and 8-2 defines basic dimensions for standard and threads. So you do not need to. Our job is not to define the threads. Our job is to select those threads. Okay, guys? Keep in mind, we are not thread experts, and we are mechanical engineers, and our job is to, based on our needs, we select appropriate pieces of threads that we can buy from the nearby vendors. This is our job, and our job is not to design these threads. So there are some experts, they work for us to design this. So this is geometry. And so usually this is a flat top. It is also this root is a flat also, and so they have some conventions. So you can see the P, and this is so this is the DP. DP is pitch diameter. So this D is major diameter, and DR is a root diameter or called minor diameter. So H is height, and so you can see this is a height, total height. And there is the actual height of this the tools is also given as 5/8 inch. So this is 1/4 inch. And so here the top is given here also. And they have their own convention. Okay, our job is to understand and the relationship between each of these concepts. Questions regarding this slide? This is for external thread. That means here is this is the bolt. Is a bolt body, and on this side we have threads. These threads goes this way. External threads. Questions? No question? No question. So these are the diameters and areas for metric threads. So nominal major diameter and the pitch diameter. And so these two values, the pitch diameter usually is the most important one, and you need to focus on these. So for the cross pitch series, 5 pitch series, and the thread stress area, and AR. And AR is very, very important. And what is AR? I'm going to tell you guys. What is AR? I want you guys to know this. AT, thread. And it means that the tensile stress area. So this is tensile stress area, AR. It means that it is area of an unthreaded rod with the same tensile strength as a threaded rod. Okay? So it is an effective area of a threaded rod to be used for stress calculation. And you can just imagine, for here, if you see this one, that means for this rod, I don't have any teeth on it. Right? But this guy has the same strength as the rod that have teeth. So just we just think this one is imaginary number. You can see for all these sides and this nominal major diameter and thread per inch, if these three columns info are most important, and then you can check the tensile stress area. So when you want to buy things, this is the threads from the vendor. Usually you check these three columns, and then you will see if this AR, AT is good enough or not. Okay, questions? Also, these are two slides I will not talk, but so you need to know. See, so this after we finish our analysis, and then we come here, and this is usually called this is vendor's catalog. and we come here to see which one satisfy our needs. And then we just buy it. Okay, so I want you guys to know this is the tensile stress area, and you are supposed to be able to use your own language to tell me what is the ATA. So the diameter of this unthreaded rod is average of the pitch diameter and the minor diameter of the threaded rod, the diameter of unthreaded rod. So this is we can use this one to approximate it. Average of the pitch diameter and the minor diameter. So here we talk about this is a square and acme is the stress. So this is a square. This is what just Aiden asked. So this is a square teeth. We have two teeth here. So you can see this is still we call this one as a P, and P is a pitch. And pitch means that we draw a line on this line. So here this is a tooth thickness or tooth width equals the gap between the adjacent teeth. So this is called the pitch. Here is another one. So here is just this is a square. This is a trapezoid. So we also call this is the P, the same meaning of P, but here it is a 29 degree, but this one is 19 degree. These are preferred pitches for the acme is a thread. And so this is D is a diameter and P is a pitch. P is a pitch. Pitch means that it's here, right? It's a longitudinal value that measures the width of the teeth, the tooth, and the gap of the tooth. Questions so far regarding the geometry of how many C threads and also the square threads and the acme threads? Any questions? No question? Okay, then we talk about mechanics. So mechanics of is a power screw. So you can see this is a screw. So this is a screw. And we can just rotate this guy, and then we can transmit the torque to this shaft. So power screw are used to change angular motion into linear motion. So we rotate this one, right? We rotate it this way. So this one can be rotated. If we rotate this one, this guy will be moving in that way. Or so if this guy is rotating, and so this guy will be translating vertically. So this is changing angular motion into the linear motion from one shaft to another shaft. Usually transmits the power, the torque that transmits the power. For example, include the vices and presses and jacks and lead screws on lathes. So here, so this is a photo of the true device, and then we can look at this is a schematic representation. So mechanics of power, the screw. So this is a nut and can be a plate, right? So this is a nut can be a plate also. This is a bolt. And find expression for torque required to raise or lower a load. So this is unroll one turn of the thread, and this is treat the thread as an inclined is a plane. Then do force analysis. And here you can see. So this is one tooth. This is one tooth, and he sees this is inclination angle, and so this is from this lower and to the higher. So we can just think for one thread, for one revolution, we can just straighten it. If we straighten it, we can just use this figure to denote for example, from here and to go here and go here and come here. Look at my mouse, okay? So I can use this figure to mimic. This is the thread from this point, for example, from this point and go up and still go up and go back to this is the unthreaded rod and go back here. So this is one revolution. Okay, this one revolution. I can just imagine I just straighten it, and the straighten it I can use. So this is the diameter to mimic. It's one revolution of the thread. Did that make sense? From here, go up along this slope, then go there, and behind this is the unthreaded rod, and go here. This is one revolution. For one revolution, we know that this is L, this is L, so this is L. This actually is L is a pitch from here to here, and so this is how long from here. So this is we know is one revolution. Right? In one revolution, the length equals, this is dm is the minor diameter multiplied by this is the pi. So this is peripheral length, and we can use this triangle to solve. And so here is a force. So here is a force. Suppose we rotate this way. So this is the friction force F multiplied by N. N is the normal force, is the friction. So this is a PR here. PR is a radial force. And so these three guys, and 1, 2, 3, 4. These are 4 guys, and they are in the balance. So for this one, and for this one, look at this, the direction of the friction. And so we are rotating. So here. So this is knot. So the knot is rotating this way, right? Knot is rotating this way. And so that's the reason we have opposite direction for the friction force. So the knot rotates this way. That means we are losing. We are losing the knot. Here, we are tightening. Here, we are losing. Understand? Because the friction coefficient and the friction force is always what? Meaning audio might not be fully recorded. I'm sorry, guys. I did not do anything. Okay, so one is tightening. This is the tightening. So this is losing. That's the reason. And the friction force, they are acting in 2 opposite directions. Okay, then we just use the free body diagram for reading the load. For reading the load, I'm talking about this one, right? For reading the load, and we have because suppose this one is in the state of equilibrium, and we know the force. We know we have 2 force balance equations for Fx and Fy. Fx must be equal to 0. Fy must be equal to 0. Otherwise, and so this is assembly of the nut and bolt, they are not stable. But for lowering the load, and we have 2 separate equations. So they are different because the friction direction is changed. So we have these equations. So lambda is inclination angle. So you can see here, lambda is the inclination angle. So this is a lambda. Lambda is inclination angle. Also here, also here. So estimate N and solve for P to raise and lower the load. The N here, okay? So you can see N is in both of these 2 equations. N And for here, let's talk about this one. N is here, number is given, N here, number is given, the PR, F. So this is, we can establish the relationship between the PR and F. Questions? Nice. Are you okay with this equation? Let me ask you, what is input and what is output for this equation? So this equation establishes the relationship between the PR, and PR is a force that is needed and to raise this is the load by F. What? F is the actual load I want to have, actual force. Final, not final. The actual force I want to have. So if I want to have this kind of force, this is the load I need to have. So this is the force I should have. The PR is a load. This is a PL. This is a PR and PL. Questions? Now then divide the numerator and denominator by cosine lambda and use relationship with this one. We can get a PR. We just use the PR here because we have a number value. Number value. We know what the number value is, but we want to use the DM because DM is more convenient for us, right? DM is a input value, is a known value already. You have sense, guys? The force. How much force you need to have to raise it? And how much force you need to apply and to lower it? And this F is resultant absolute F I want to have. So after you get this P, and you can get this is the torque. What? The torque. So this is F. F, the force multiplied by dm. Any question, guys? Questions, comments, remarks? Torque equals the force multiplied by half of the diameter. Half the diameter, we are using this value, okay? You understand, guys? So PR equals this. This guy multiplied by half dm equals this. Questions? No question. Okay, you can see. So this is the needed torque. They are related to the F you want. This is F is might be their actual load after you finish assembly. So it depends upon how much, depending upon F, and you know what is the torque you need to apply. Okay, so then we can look at the self-locking condition. The lower, okay, so this is from here. Is a lower and lower torque. Lower torque means that the torque that is needed if you want to lower, and so this is disassembled and this both are not. if the lower torque is negative, if the lower torque is lower, the torque is usually the positive, right, guys? You guys agree? And the torque is because we consider the direction already. And so if the lower the TL is a negative, what does that mean? If the lowering torque is a negative, the load will lower itself by causing the screw to spin without any external effort. If the lowering torque is a positive, the screw is self-locking. If the lower torque is a positive, the screw is a self-locking. Self-locking means that it's locked. You cannot lose it. Then you can see, then come back, under what condition we can make sure TL is positive. If the TL is positive, and so we just make sure this is greater than 0. That means this guy is greater than L. Questions? Also, we know that based on the geometry, tangent and lambda inclination angle, it equals the length for one revolution divided by length. I'm sorry, the L. L is the height, is a pitch, actually is a pitch. Divided by one revolution. How long it is one revolution? Peripheral length, high EM. L. Here is L, guys. You can see. And so this is L. So this L is the pitch. The pitch. So L divided by the pi dm equals tangent lambda, the self-law condition can be seen to only involve the coefficient of friction and the lead angle. Lead angle is the number. Frictional coefficient is the lambda and the lead angle. If this inclination is satisfied, that means this condition will be satisfied. You understand, guys? Are you following me closely, guys? If you are confused, you need to ask me. Okay? Otherwise, I assume you are following me closely, because I cannot read your mind. Right? If I can read your mind, that would be good. I would have magic. I know what I will guys doing. Are you doing material science things? Are you doing manufacturer abacus modeling? I cannot. So that's the reason we need to communicate. Communication is very, very important. So this equation and this equation, they are equivalent. Why? Because we know that, right? So tangent lambda is written as the pitch, the distance between two adjacent teeth divided by the revolution. So the peripheral for one revolution, the pi dm. So then this is the inequality condition for self-locking. And then we introduce the lambda. Then it's F. If the F is greater than tangent lambda, it's self-lock. Self-lock means that you almost have no chance to lower it. Then what you do? Break it. No, sorry, should not say that. You can just change it, okay? How to do that? Make sure this F is lower. How to do that? Add the lubricants. Single way to add the lubricants between the teeth and this in the threads. Questions? No question? The power screw efficiency. This is one. The torque needed to raise the load with no friction loss can be found from this equation. And if F equals 0, and for this is H8-1 here. If F equals 0, okay? If F equals usually the friction, if we overcome the friction, and usually we waste our energy and force. You guys agree? Because friction is usually not good. So in an idealized case, if F equals 0, this TR can be rewritten as using this one. Then the friction efficient of power screw is therefore is using this ratio to denote the E equals this case without force and with force, and then use this equation. You can see we have a lot of very small tiny equations. But one good news is that I will not test your understanding of this. I will not ask you guys to memorize it. Okay. However, if I want to ask you to use your own language to explain, you should be able to do that. Question regarding these two equations. So this one is the idealized case in which we do not have F equals 0. That is idealized case, but it does not exist. And then we can use this one to calculate the efficiency. Because the friction, while we overcome friction, we usually consume more energy and consume more force. It does not give us anything good. So this acme is thread. Acme thread is not this square, but it is some angle there. Excuse me. So if acme threads are used instead of square threads, the thread angle creates a wedging action. This is wedging. The friction components are increased. The torque necessary to raise the load or tightening a screw, and we use this equation. I will not derive it. I will not show you derivation, but and you should be able to know it's here. Okay, so this is alpha. So this is the angle. This is alpha is a thread angle. Alpha plays an important role also, not just F. For the F, this is a lambda. Lambda is an inclination angle. So you can see, know this one. If there is a need, and you can come back and to use this equation to calculate the required torque and to raise it in order to have this F, this axle load. The collar friction. The collar friction, you can see, and here, so this is collar, and so this is a knot, and so this is a bolt. So additional component we can because the collar, okay, collar, and we suppose if the collar here, this is collar, if the collar is in close contact with this plate, then definitely, excuse me, and definitely there is a friction. So additional torque, component of torque is often needed to account for the friction between a collar and the load, between the collar and the load. Assuming the load is concentrated as the mean collar diameter load, and we just have an assumption. And so this here, and this is the TC equals FC DC2. So this is for the torque that you need to have to overcome this is the friction that is exerted by the friction between the collar and the plate. So this equation. So the stress in bodies of the power screws. The maximum normal shear stress in the torsion of the screw body, we can use